the sun's true position is actually halfway between the center and the edge, not at the hub, as Herschel indicated in his drawing. So we're getting a fuller picture of the galaxy, but there's still a lot to understand about it. Like, how did it form? Or why did it form in a particular way that it formed? What kind of stars make up the galaxy? Are they all the same ages? Are they all from the same place? So we continue to look and do research, and we found that um, the galaxy has a basic structure like you see here. It has a thin disk, stellar halo, and a center bulge. And you can see that in the images up here. In the center here, we have our central bulge, right? They show you on the right the thin layer of dust. They show you the globular clusters that usually are in the halo, right? They show you the diameters of the thin disk and the thick part of the disk, right? And we also should note that the central bulge is not just a bulge, like a spherical bulge. It tends to be peanut shaped, about 10,000 light years in radius, with a dense concentration of very old stars. So we know older stars from our previous lectures are going to be yellow. So that's where you get that yellow bar, that yellow hue when you're looking at a lot of the I guess you could say, realizations of the galaxy, right? And the stellar halo extends to about 150,000 plus light years, right? It consists of old, faint stars in spherical distribution. Okay. The thin disk is about, as we mentioned before, it's about 100,000 light years wide, 2,000 light years thick, and it's full of young stars, gas, dust in the spiral arms. All right, now let's get back to the galaxy. About 13 billion years ago, that's this image here, right? We just had like kind of a spherical protogalactic cloud that begins to collapse. Remember, we had this huge cloud of hydrogen, and this is back 13 billion years ago. So there hasn't been a lot of heavy element production. It's mainly just hydrogen and helium gas, right? The gases collapsed into a rotating disk, and it took about a few hundred years, all right, and enriched with heavy elements from previous stars. We started a long time ago, so we've had stars that have went through their life cycle and built heavier elements and released them. They stayed within that system. Then we have what's predicted, the future collision, right? And in 4 billion years, we're expected for our galaxy to merge with the Andromeda galaxy. The result's going to be this huge, giant elliptical galaxy. It's going to kind of, as you see here in the bottom picture, right? Now, in this picture right here, you see these streams of stars and dust and matter. These are called tidal streams, right? So it's a combination of the original proto-galactic cloud spinning into a disk, moving around, picking, merging with other astronomical objects, right? And all of this came together to shape the galaxy that we see today. Okay, so let's talk a little bit more in depth about the shape. Okay, how did the spiral arms form? What happens is in the center, the rotation is faster, right? That makes sense. Materials closer to the center orbit faster, stretching the gas clouds out into these spiral shapes, kind of stretching them out. And as time goes on, the spirals begin to, first you get like the top one. You start off with this, just kind of like these little blotches of light in here. As the spinning continues, right, and they kind of come close to the center, they start to get stretched out, and you start to notice a little bit of spiral shapes forming. And then on the third one, you see them even more developed. And finally, you see a situation here where you have these well laid out spiral patterns. Okay, so looking at this, we could say the first image is around 13 billion years ago. These two in the middle are somewhere around 10 billion years, where you get this fuzzy, indistinct spiral arms beginning to form. That's these two in the middle. And then 5 billion years ago, you get kind of like this well-defined spirals that you see here. Okay. All right. So now let's look a little bit deeper into that spiral structure. Where are we exactly? Well, the spiral arms, there's two major arms there, right? And let's go back one, right? You see at the end of the bars, you have two major arms that spin off, right? And then you have all these little spurs and things that shoot off of those, right? The sun's location is actually in an area called the Orion Cygnus Spur. It's about 10,000 light years long, right? So the sun is over here. You see, this is the Orion Spur right here. We're right over here. Okay, all right. The Orion Spur, let's see a little bit more information about that. The galaxy doesn't rotate like a solid wheel. The inner regions, again, orbit faster than the outer regions, and following Kepler's third law. And that's going to come into play in a minute. We start talking about getting deeper into this concepts. Okay, so we did mention that we have some very old stars that are mainly in the center in the bar shape, and we have some very new stars. So let's talk about them. They were categorized as popular one stars, right? Popular one stars location is in a disk and a spiral arm. So those are the younger, hotter stars, right? Wide range, some still forming, right? The heavy elements in them about 1 to 4% of the mass. Okay, they orbit nearly circular. And examples: the sun, O and B stars, open clusters. That's what popular one stars. Popular two stars, those are the ones in the halo, the globular clusters. Should say yeah. And their age is about 11 to 30, much older, 11 to 13 billion years, right? They have less heavy elements, about 1/100, because when they were formed, there was a much lower percentage of stars that had lived their life cycle, so there was a much lower percentage of the elements that those stars would create, in their life cycle. All right. Okay. Heavy elements created in stars recycle into new generations. Older stars formed when the galaxy was metal poor, right? They just had mainly hydrogen, helium, right? And that's why you have that distinction between the older stars and the newer stars. All right. So now let's talk about a very special star. And we're gonna finish up with that imbalance I was telling you about. I did hint at it a few times. So a very special star is our sun, right? Its approximate, and listen to this, its approximate speed, orbital speed, is between 200 and 220 kilometers per second around the galactic center, right? The distance from the center is about 26,000 light years. Okay. And you may say, well, what is this 95%, 5%? Well, we're going to get into that. The dark matter problem. And this is where we start to speak about this, because we actually use the sun to analyze the situation with this matter imbalance, right? And we're actually going to walk through an example of how to do that. Okay. So outer objects, and the basic problem is the outer objects of the galaxy orbit way too fast to be held by the visible matter that we see. In fact, 95% of the galaxy's mass is invisible dark matter, right? While only 5% is luminous matter the matter we can see, the stars, the gas, and the dust. Okay. So let's not take their word for it. Let's actually do a calculation of our own. That means we're going to consider the mass from the center of the galaxy to the orbit of the sun. There's a lot more past the orbit of the sun, but we're just going to use this as we're going to take like a sample of the galaxy, right? And even within a sample, we're going to see this discrepancy, and you'll understand more how that indicates certain things about dark matter. So let's go through the equation. It's a cubed equals the sum of the galaxy and the mass times p squared, where m, is the total mass of the galaxy, m sun is the mass of the sun, a is a semi-major axis on the sun's orbit, approximately 26,000 light years, and p is the period of the sun's orbit around the galactic center, roughly about 230 to 250 million years. Okay, right? We rearrange rearranging this to solve this original equation for the galactic mass. We have the mass of the galaxy equals a cubed over p squared minus the mass of the sun. Now, the mass of the sun is so tiny compared to the mass of the galaxy, so it's negligible. So we're just going to drop that. It's almost like being zero. Okay. We go ahead and we calculating the mass of the sun inside the mass of the galaxy inside the sun's orbit. And step one, we calculate a cubed. We go ahead and do that, plug in our values, we get this. Step two, we calculate p squared. We plug in our values, we get that value out. And step three, we divide to find the mass, right? So we say mass of the galaxy equals a cubed divided by p squared. We end up with the mass of the galaxy is approximately 1.08 times 10 to the 8 solar masses. The mass of the galaxy interior to the sun's orbit is approximately 1 times 10 to the 11th solar masses, or 100 billion solar masses, right? And it is significantly greater than the combined mass of all the stars, gas, all the visible matter that we see within that area, and thus within the same region. Okay, now let's look at it from a same problem, but from a different mathematical perspective. If we calculate the velocity, theoretical orbit of the sun around the galaxy, right? We should, with the visible mass only, right? Visible matter only, the velocity should be about 100 to 120 kilometers per second. If it was just the visible mass that we saw, due to the gravity of that visible mass. But what we observed is the velocity of the sun is about 200 to 220, right? And they find that what they expect, if it was just a visible matter, that the velocities would drop off, right? So what's the takeaway from this? Calculating mass this way for the sun and other objects shown that orbital speeds in our galaxy remain high, flat rotation curves, as you saw, much faster than expected from the visible matter alone. Right. Two, the discrepancy implies a vast halo of unseen mass called dark matter. Right.